Okay, this is page 53 of the complex numbers booklet. Okay, we're going to be looking at the binomial expansion a plus b to the power of n. And what you'll notice is that the coefficients of that expansion can be found by using Pascal's triangle. I'll look over here at Pascal's triangle. So Pascal's triangle. Now, Pascal's triangle starts with a 1 at the top, and then we've got a 1 on either side, and then we've got a 1 and a 1 on the outside. So you've got all 1s on the outside of Pascal's triangle. So you start with a 1 at the top, and then another 2 1s, then 1. And what happens is each number in the triangle, in each subsequent row now, is the sum of the two numbers above, except for the first and last term in each row, which is 1. So the first and last term in each row has to be 1, but the sum of the two numbers above equals the number underneath. So again, we've got a 1 over here, but 1 plus 2 is 3, 2 plus 1 is 3, and we've got a 1 on the end again. Here I've got a 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and a 1 on the end. And again here, a 1, then we've got 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and a 1. Now that is Pascal's triangle. Now what you'll notice about Pascal's triangle is that it gives you the coefficients of the binomial expansion a plus b to the power of n. So if we just look at our first one, which is a plus b to the power of 0, we know that that equals 1. Now a plus b to the power of 1 is a plus b, which happens to be 1a plus 1b. Notice the coefficients here is 1. Coefficients here of a and b are 1 and 1. Now if we expand a squared, a plus b all squared, we get a squared, or 1a squared, plus, remember it's 2ab, plus b squared, which is just 1b squared. Notice the coefficients are 1, 2, 1, 1, 2, 1. Now, what you'll notice is when you do this expansion, our highest power is 2. Notice we start with a squared, then we drop a power of a to get a, and we introduce one power of b, and then we drop another power of a and go one higher in the powers of b. Same thing with the expansion of a plus b cubed. The coefficients will be 1, 3, 3, and 1, so you'll get 4 terms. But the first term will be the highest power of a, which is a cubed, plus the coefficient of the next term is 3. Then we drop one power of a to get a squared and introduce one power of b. Next coefficient is 3. Drop a power of a and you get a, and introduce another power of b. You get b squared. And the last coefficient is 1, and you'll drop one power of a and go up one power of b, and you'll get 1b cubed. Okay, now the next expansion, you've got 1a to the power of 4. These are our coefficients. Then the next coefficient is 4 plus 4. Drop a power of a, go up one power of b. The next coefficient is 6. Down one power of a, up one power of b. Again, 4, down one power of a, up one power of b, and the last coefficient is 1. And you drop a power of a, which gives you no a's, and increase one power of b, which gives you b to the power of 4. And with the 1a plus b to the power of 5, you've got 1a5 plus 5a4b. So we're just dropping one power of a, going up one power of b. Next coefficient's 10, so you get 10a cubed b squared. Another 10, 10a squared b cubed. Then you've got 5ab4 and 1b5. Okay, so that's binomial expansions, and the coefficients of the binomial expansions follow Pascal's triangle. Okay, now you'll also notice here how we've got a plus b squared. The second term starts with a 2. A plus b cubed, the coefficient of the second term is a 3. A plus b to the power of 4, the coefficient of the second term is 4. A plus b to the power of 5, the coefficient of the second term is a 5. Okay, now let's do an example. Our first example is to expand cos theta plus I sine theta cubed using de Moivre's theorem. Now, using de Moivre's theorem, we've got cos theta plus I sine theta cubed is just cos 3 theta plus I sine 3 theta. Now we're also going to expand cos theta plus I sine theta cubed using Pascal's triangle. So we'll start with cos theta plus I sine theta cubed. So we'll be using this row of the triangle. So it's the first term is cubed, so we get cos cubed theta plus 3 lots of, now we drop 1 power of this, so we've got cos squared theta times, introduce one of these, I sine theta, plus then we have 3 cos theta, dropping 1 power here, but introducing another one here, times I squared sine squared theta. So notice our coefficients, 1, 3, 3, this last coefficient's 1, and it's just this term cubed, and we've got I cubed sine cubed theta. Now, what we're going to do is collect any real terms. So remember I squared is -1, so this will be, so what we've got here, real terms, cos cubed theta, I squared is -1, so we get -1 times 3, so we get -3 cos theta sine squared theta, -3 cos theta sine squared theta. Then we've got plus, now looking at the terms with I, we've got I times 3 cos squared theta times sine theta. And remember I squared is -1, so this will be minus I. So I'm going to put a minus then. So minus, and we've got an I out there. So that is the same as minus I sine cubed theta. So I've got the I there, so I've got minus sine cubed theta. Sorry, I'll just fix that up, one sec. What I need to do is I want to make the real terms in terms of cos theta only and the imaginary term in terms of sine theta only. So we've got cos cubed theta minus 3 times cos theta. Now we know that sine squared theta is 1 minus cos squared theta. That's using the result that sine squared theta plus cos squared theta is 1. Then we've got plus I. We want to make this all in terms of sine theta, so we've got 3 lots of 1 minus sine squared theta times sine theta minus sine cubed theta. Now this is equal to cos cubed theta minus 3 cos theta plus 3 cos cubed theta. Then we've got plus I times, now we've got 3 sine theta, and we've got minus 3 sine cubed theta, and then minus another sine cubed theta. So we're just expanding this. Remember the sine theta could go in the front, so we've got 3 sine theta minus 3 sine cubed theta minus sine cubed theta. Okay, now that is equal to 4 cos cubed theta minus 3 cos theta plus I times 3 sine theta minus 4 sine cubed theta. Okay, now that is our binomial expansion for cos theta plus I sine cubed theta. Hence we have to show that cos 3 theta equals 4 cos cubed theta minus 3 cos theta. Now we've got 2 expansions for cos theta plus I sine theta cubed. It equals this here, and it also equals that. Now the underlined bits are the real parts. So if we equate, so equating real parts of A, we get that therefore cos 3 theta equals 4 cos cubed theta minus 3 cos theta. And if we look at equating imaginary parts of A, we will get that sine 3 theta. We get that sine 3 theta equals 3 sine theta minus 4 sine cubed theta. So now for the last part here, we have to therefore show that tan 3 theta is 3 tan theta minus tan cubed theta over 1 minus 3 tan squared theta. Now we know that tan of 3 theta is sine 3 theta over cos 3 theta. Now we can substitute in our expressions there, which is 3 sine theta minus 4 sine cubed theta over 4 cos cubed theta minus 3 cos theta. Now, we're trying to end up with an expression in tan. We know that sine over cos is tan. And notice we've got a tan cubed theta. So if we divide through each term by cos cubed theta, we get the following. So we'll have 3 sine theta over cos cubed theta. That gives us 3 tan theta over cos squared theta, which will give us times sec squared theta. Because note that 1 over cos theta is sec theta. Okay, minus, now if we've got 4 sine cubed theta over cos cubed theta, we get 4 tan cubed theta. Then we go over. Now 4 cos cubed theta divided by cos cubed theta is 4. And 3 cos theta over cos cubed theta will be 3 over cos squared theta, which is 3 times sec squared theta. Now, we also know that from our 2-unit results that 1 plus tan squared theta is equal to sec squared theta. So making that replacement for sec squared theta, we get that tan theta times 1 plus tan squared theta minus 4 tan cubed theta over 4 minus 3 times 1 plus tan squared theta. That is equal to, now we're going to expand, and we get 3 tan theta plus 3 tan cubed theta minus 4 tan cubed theta over 4 minus 3 minus 3 tan squared theta. And that simplifies to, and we've got 3 tan theta, that doesn't cancel with anything. And we've got 3 tan cubed theta minus 4 tan cubed theta, which is minus tan cubed theta, over 4 minus 3 is 1, and we've got minus 3 tan squared theta. And that's the result that we're meant to get. So that's the end of page 53. Now the next part of the question says to solve x cubed plus 3x squared minus 3x minus 1 equals 0 using the substitution x equals tan theta. So we'll do that substitution now. So we've got tan cubed theta plus 3 times tan squared theta minus 3 tan theta minus 1 is equal to 0. Now if we look back at our results from part 3, and I'm just going to put that here, notice we've got tan 3 theta is 3 tan theta minus tan cubed theta, so the tan theta gets grouped with the tan cubed theta and the 1 gets grouped with the 3 tan squared theta. So that's what we're going to group together over here. So I'm going to keep the tan cubed theta with the 3 tan theta on the left, and I'm going to take the 1 over and the 3 tan squared theta over to the other side. So we've got that tan cubed theta minus 3 tan theta is 1 minus 3 tan squared theta. Now dividing by both sides by 1 minus 3 tan squared theta, so dividing both sides by 1 minus 3 tan squared theta, we get tan cubed theta minus 3 tan theta over 1 minus 3 tan squared theta. Now that over itself is 1. So we're dividing by 1 minus 3 tan squared theta. Now, this is almost the same as what the result that we proved in part 2. If you look at the result that we proved in part B, we've got tan 3 theta is 3 tan theta minus tan cubed theta over 1 minus 3 tan squared theta. So the denominators are the same, but the numerators are in reverse. So if we put in negative, we've got that negative bracket 3 tan theta minus tan cubed theta over 1 minus 3 tan squared theta is equal to 1. Okay, just checking that that's the same. Minus 3 tan theta plus tan cubed theta, that is the same. Now what we can do is just take the negative, like multiply both sides by -1. We're just taking the negative to the other side. We end up with 3 tan theta minus tan cubed theta over 1 minus 3 tan squared theta is -1. Now we know from part B that 3 tan theta minus tan cubed theta over 1 minus 3 tan squared theta is the same as tan 3 theta. So we replace this therefore with tan 3 theta equals -1. Now to solve this we're going to use general solutions. So Remember, general solution for tan, the rule is this: tan theta equals tan alpha. So if tan theta equals tan alpha, where alpha is acute, then theta equals 180n or pi n plus alpha. Okay, so that's the general result, or the general solution for tan theta. Okay, so writing it in that form, so therefore tan 3 theta equals tan. Now we know that tan 45 is 1, but tan of negative 45 is negative 1. 45 is pi on 4, so tan minus pi on 4. So now writing out the general solution. So therefore 3 theta is 180n or pi n plus negative pi on 4 plus whatever the alpha is for any integer n. So therefore 3 theta is equal to the following. Now if we let n equal, remember n is an integer, so it's 0 or plus or minus 1. Any integer n which is 0, plus or minus 1, comma, plus or minus 2, etc., etc. Okay, so we've got, when n is 0, we get minus pi on 4. When n is 1, we get pi minus pi on 4. When n is negative 1, we get minus pi on 4. When n is 2, we get 2 pi plus minus pi on 4, which is 2 pi minus pi on 4. When n is negative 2, we get negative 2 pi minus pi on 4, etc. Okay, we can also do when n is 3, for example, we get 3 pi minus pi on 4, and I'm not going to do any more. Okay, now let's just simplify what those are. We've got minus pi on 4, we've got minus 3 pi, sorry, no, we don't have minus 3 pi. That's 1 minus a quarter, which is 3 pi on 4. Then we've got minus 5 pi on 4 here. And here we've got 2 pi minus a quarter pi is 7 pi on 4, because it's 1 3/4. And we've got minus 9 pi on 4. And we've got 12, 11 pi on 4. Now I'm going to put them into some order. They're sort of out of order. I could put the negative ones, I suppose, together and the positive ones together. So I've got that I'm going to get them in order. Negative 9 pi on 4 minus 5 pi on 4 minus pi on 4. And then I think we've got 3 pi on 4, 7 pi on 4, 11 pi on 4. You can see that the denominator increases by 4 pi, okay? So, and now that's what 3 pi is. So therefore, 3 theta is. So therefore, theta dividing through by 3, we get minus 9 pi on 4. Now we're looking for, I'll just fix that in a minute, minus 5 pi on 12, minus pi on 12, 3 pi on 12, which is a quarter pi. We've got 7 pi on 12, 11 pi on 12, because we're dividing each of these by 3. Now we're looking only for 3 solutions because we've got a cubic equation. So some of these are actually repeats of each other. So I'm just going to draw a quick little diagram here. Remember with with principal arguments, we want, sorry, just found a little mistake here. This is minus 9 pi on 12. I've just noticed that there. Okay, now as I was saying, it's a cubic up here, and there should only be 3 solutions. And here I've got 1, 2, 3, 4, 5, 6 solutions. So some of these are actually duplicate solutions. So let's just sketch where they are. 3 pi on 12 is a quarter pi, and this is 0 pi, this is pi on 2, so 3 pi on 12 would be here, which is, I'll just write it as 3 pi on 12, but remember it's the same as pi on 4, okay? And the next one, 7 pi on 12, it's a bit more than pi on 2, it's a bit more than half, so we've got 7 pi on 12 would be about here. and 11 pi on 12 is not quite 1 pi, okay? And we've got minus pi on 12, which would be here. And we've got, what else? Minus 5 pi on 12 would be here. And we've got minus 9 pi on 12, which would be about there. Now, you might say that all these look different. But remember, our solution, we're letting x equal tan theta. So the thing is, in quadrants 1 and 3, tan is positive. So if we just look at what our solutions are, so remember we're looking for x equals tan theta. Now, we know that tan of minus tan of 3 pi on 12, which is tan of pi on 4. Okay, so tan of 3 pi on 12 is actually, remember you've got an acute angle of 3 pi on 12 there. It's actually the same as this angle here, equals tan of minus 9 pi on 12. So you only need one of those solutions. So just to simplify it, it's tan of pi on 4. So that's one of my solutions. Also notice that tan of, so these two give you the same result. The next one I'll look at is tan of, let's say, 7 pi on 12. Now the acute angle here would be 5 pi on 12. Tan is negative in quadrant 2 and it's also negative in quadrant 4. So the tan of 7 pi on 12 is actually going to be the same as the tan of minus 5 pi on 12. Okay, because they're in, sorry, you can't see that. So the tan of 7 pi on 12 will equal the tan of minus 5 pi on 12 because they've both got the same acute angle in those quadrants, because the acute angle is actually 5 pi on 12 in both quadrants. Okay, so therefore you only need one of those solutions. Okay, and the other thing that we know is that tan of 11 pi on 12, now that's quadrant 2, and so in quadrant 2 tan is negative. It's actually, it will give you the same result as tan of minus pi on 12. Okay, so therefore, now tan of minus pi on 12 actually happens to be the same as minus tan pi on 12, because we know that in quadrant 4, so in quadrant 4, we know that tan of negative theta equals negative tan theta. So I can actually do the same thing here as well. Tan of minus 5 pi on 12 is the same as minus tan of 5 pi on 12. So therefore, x equals the following. My three solutions will be tan of pi on 4, negative tan 5 pi on 12, and negative tan of pi on 12. Now we know that tan pi on 4 happens to be 1. Okay, so tan pi on 4 is 1. We've got negative tan of 5 pi on 12 and negative tan of pi on 12. Now the reason we use the negative tan 5 pi on 12 is the 5 pi on 12 is a smaller angle than the 7 pi on 12. And the reason we don't use 11 pi on 12 and we use negative tan pi on 12 is that pi on 12 is smaller than 11 pi on 12. So therefore these are your solutions to that equation. Okay, so they're the solutions to that cubic up there. Now for the last part of the question, you have to show that tan pi on 12 times tan 5 pi on 12 equals 1. It seems that these roots have been multiplied. Now there are 3 roots to this equation. So I'm just going to look at this equation again. We've got x cubed plus 3x squared minus 3x minus 1 equals 0. Now I'm going to look at the product of my roots. Now my roots are here, okay? So 1 times negative tan 5 pi on 12 times negative tan pi on 12. Remember, product of roots is C on A. So a negative times a negative is a positive, and multiplying these by 1, the 1 just goes. So therefore tan of 5 pi on 12 times tan of pi on 12. Now in this equation, A is 1, B is 3, C is negative 3. Okay, so it's negative 3. Sorry, just a little error there. It's a cubic, so the product of the roots is minus D on A. Sorry about that. So C on A is product of roots 3 at a time. Okay, so 1 at a time, sum of roots is minus B on A, product of roots 2 at a time is C on A, and 3 at a time, product of roots, or sum of roots 3 at a time, or product of roots is minus D on A. So sorry for that. That's why I wasn't getting that result as well. So product of roots, that times that is minus D on A. In this case, D is negative 1, so it's minus negative 1 over A is 1. So therefore, tan of 5 pi on 12 times tan of pi on 12 is 1 on 1, which is 1, and therefore we've proven that result. Therefore, we've shown that tan pi on 12 times tan 5 pi on 12 equals 1. That's the end of the example on page 54.